Symmetric encryption is used to protect the confidentiality of communication since it is fast. As we are going to see, there are several symmetric encryption systems. They all use a secret key that should be shared between the communicating parties. In this video, after a short introduction on symmetric encryption, I will present a totally unbreakable symmetric encryption system, which is called the one-time pad. This encryption system is unbreakable, but it is hard to use in practice. Nevertheless, it's a very important encryption system since it is at the basis of stream ciphers, which are encryption systems inspired from the one-time pad. As I said, symmetric encryption algorithms are used to encrypt communications because the encryption-decryption procedures are fast. The message is encrypted according to a special encryption algorithm using a secret encryption key. And the encrypted message is decrypted with the same key. A cipher is an encryption system, and I can formally define it as follows. A cipher is a pair of algorithms where E is the encryption algorithm and D is the decryption algorithm. Input of the encryption algorithm is a key and a plain text message to be encrypted. The output is a ciphertext. Input of the decryption algorithm is a key and a ciphertext message to be decrypted. And output is a plain text. Decryption with key K of the encryption of message M with key K gives back the message M. This animation will illustrate what I have said. Bob and Alice are the communicating parties. They share a secret key. Bob encrypts the message he wants to send to Alice with the secret key. Bob sends the encrypted message to Alice. Alice decrypts the message with the secret key. Please note that this scheme says nothing on how the secret key is shared between Alice and Bob. We will answer to that question later in this course. The one-time pad defined by Vernam in 1917 is based on two important assumptions. First, the message and the key are of the same length. Second, the key is truly random. Third, the key must serve only once. It must never be reused. Encryption is very simple. It is done by combining the plain text with the key with a XOR operation. And decryption is done by combining the ciphertext with the key with a XOR operation. The XOR operation is such an important operation in cryptography that I remind you of its properties. It is commutative and associative. Here, A and B denote two bit strings of the same length. Its identity element is 0. 0 here refers to a bit string of any length where all bits are equal to 0. Each element is its own inverse. That is, if I XOR A with A, then I obtain 0. These properties explain why the XOR of the ciphertext with the key gives the original plaintext M. Ciphertext is equal to K XORed with M. Plaintext is equal to K XORed with C. If I substitute C in the second equation with K XORed with M, then I obtain that M is equal to K XORed with K XORed with M, which is in fact equal to M. One-time pad is said to be perfectly secure, and it is the only encryption scheme which is perfectly secure, that is, it is simply unbreakable. However, implementing for each message a shared key of the same length as the message is difficult. Difficult but not impossible. There are applications of one-time pad. One of them is the hotline that was set up between the USA and the USSR in 1963 after the Cuban Missile Crisis. During that crisis, both countries were on the verge of nuclear war. After that crisis, they realized that one of the reasons they were about to start a war was the lack of real-time communications. So both countries decided to set up this hotline where messages were encrypted using the one-time pad algorithm. And predefined keys were exchanged in advance via the embassies. I said previously that the key must serve only once. Indeed, two-time pad is totally insecure. If an attacker has a pair MC, then he can retrieve the key by a simple XOR combination as follows. The attacker simply XORs the plain text with the ciphertext to obtain the key. That's why the key must never be used again, since if it is used twice, the attacker can then directly decrypt the second message. Now you may say, okay, but this assumes that the attacker has a pair plain text ciphertext. It may not be easy to obtain a plain text and its corresponding ciphertext. Yes, this is true. But in fact, the attacker does not even need a pair MC. From two intercepted messages encrypted with the same key, the attacker can retrieve the two original messages. How can this be possible? Let me show it to you. Let us consider two intercepted messages by an eavesdropper. The eavesdropper is an attacker who simply listens to the encrypted communication. The eavesdropper intercepted C1 and C2, two ciphertexts encrypted with the same key. If the attacker XORs C1 with C2, then key K is eliminated and the result is equal to M1 XORed with M2. And it is possible to derive M1 and M2 from M1 XORed with M2, because M1 and M2 are not random messages. They have a certain structuration, and from this structuration we can deduce M1 and M2. And the easiest way to convince you is to use a graphical example. This figure shows two images, sendcache image and the smiley. And both images are encrypted with the same key K, which is a truly random image. Encrypting the sendcache image gives encrypted image C1. Encrypting the smiley gives encrypted image C2. We can visualize the result of XORing both encrypted images. The XOR operation has eliminated the key from both images and has left us with the combination of the two original images. So I hope this result convinces you that we can retrieve the two original images from the combination of the two encrypted images. So this video was about the one-time pad, the only encryption system which is perfectly secure. However, it's not a practical encryption system, since keys should be truly random, the length of the message to be encrypted, and used only once. Nevertheless, it was used in a few applications, such as for encryption of messages on the hotline between the USA and USSR. One-time pad is the basis of stream ciphers, which use a pseudo-random generator to produce a key for each message.